Hello, today I'm going over the International System of Units lecture, and we're going to be talking about a standard set of units that are common among scientists. So they're kind of speaking the same language. All right, scientific measurements are standardized through the International System of Units, or SI, a modern evolution of the metric system that utilizes a base 10 structure for easy conversions. So base 10 structure is good because everything is around the number 10. Other like a difference would be feet, right? Well, feet is not divisible by 10 inches. It's 12 inches in a foot. So that's a different base. While the system was formally adopted worldwide in 1960, its roots trace back to the original metric standards established in the late 18th century France. So we had this metric system, and now this is just a more formalized version of it. Although seven fundamental base units exist over here, the field of chemistry focuses primarily on the meter, kilogram, Kelvin, second, and mole. Despite the importance of these international standards, certain non-SI units remain in common use due to their practical convenience in specific scientific applications. So we're going to see some other units occasionally used, but these are your standards. Sometimes it's going to be better to use other units depending on what is being investigated. All right, so let's go over each of the ones that we would see normally. First one is the meter. So the meter serves as the fundamental SI unit for measuring length or linear distance. To manage extreme sizes more efficiently, metric prefixes are added to the base unit to represent different scales. So what they're talking here is like, if you only use meters, sometimes your numbers are going to get really, really big. So how many meters from Earth to the sun? Well, that's a huge number. So maybe we could say how many kilometers from here to the sun, which makes it a more manageable number, different scales. And then in this picture here, it shows the old standard for what the meter was, which was based on like the distance around the Earth and 1/10,000th of that distance or something. And now it's officially the length of a certain wavelength on the electromagnetic spectrum, just something that's a little bit more precise. So anyways, for instance, the prefix milli indicates 1,000th of a meter, while kilo represents a multiple of 1,000. Consequently, the most frequently utilized units for length in scientific and practical applications are the centimeter, meter, and kilometer. All right, let's keep going. We'll look at volume now. Scientific volume represents the three-dimensional space an object occupies and is officially measured in the SI system using the cubic meter, m cubed. So that's a meter by meter by meter. Again, volume is the amount of space that an object is taking up, as opposed to distance, right? Something different. Because the cubic meter is quite large, chemists more frequently use smaller non-SI units such as the liter or milliliter for everyday laboratory work. But you'll notice it's still a variation of this cubic meter. The milliliter and the cubic meter represent the exact same amount of space and are therefore used interchangeably when reporting measurements. So oftentimes in lab work, it makes more sense to use these other ones rather than the traditional meter cubed, especially if you're talking about volumes that are in the laboratory that are microscopic, drop size. Furthermore, because the volume of matter expands or contracts with temperature, Precise measuring tools like burettes and flasks are typically calibrated for use at 20 degrees Celsius. So when thinking about volume, you also have to consider temperature, because temperature can change the volume of an object. That's why they try and use a standard temperature here. All right, next up is mass. So the kilogram serves as the fundamental SI unit for mass and was historically defined by the mass of 1 liter of liquid water at 4 degrees Celsius. So you'll notice that these last two were all based on our original meter, and they're derivations of that meter. While mass represents the constant quantity of matter within an object, weight is a separate measure of the gravitational pull exerted on that mass, meaning weight can change depending on location while mass remains the same. My weight on Earth and the moon is different because of gravity. My mass on Earth and the moon is the same because they're two different things. In laboratory settings, scientists use various balances to measure mass, ranging from analytical balances for tiny amounts to platform balances for larger objects. Common metric units used to express these measurements include kilogram, gram, milligram, and microgram. And we're seeing these come up again, right? Kilo and milli. We saw them when we were talking about volume as well. All right, last page here. Next up is going to be temperature. Scientific temperature is a measure of the average kinetic energy of the particles within a substance. We forget this a lot. So when we say something hot is hot, it just means it has a lot of kinetic energy, a lot of motion to those molecules. If something's cold, it has slower motion to those molecules. There's not as much movement of those molecules. That's what temperature is. The SI system identifies the Kelvin as the fundamental unit of temperature, which is unique because it does not use a degree symbol and begins at absolute zero Kelvin, the point where all molecular motion theoretically ceases. So you can't actually get to 0 degrees Kelvin, but you can get within a billionth of a degree of 0 Kelvin. At 0 Kelvin, molecules stop, which, as far as we know, can't happen. While the Celsius scale is common in laboratory practice, it is defined by the freezing of and boiling points of water at 0 degrees Celsius and 100 degrees Celsius, respectively. So still not the greatest. At least it had, the Celsius scale had a reason why it started at 0 and 100, basing it off freezing and boiling water. But Kelvin is the better way to go, really. Because the two scales use intervals of the same size, a Celsius measurement can be converted to kelvins by simply adding 237.15 to the value. So easier to go from Celsius to Kelvin than it is to go from Fahrenheit to Kelvin. All right, last one here is energy. So energy is scientifically defined as the capacity to do work or produce heat. This is a standard apparatus called a calorimeter that you would find in labs, both high school and college. And what it does is it takes a sample of something and heats it in this closed container of water. And as it burns, it heats up the water, and that's going to give us a calculation for amount of energy. The joule, named after physicist James Prescott Joule, serves as the official SI unit for measuring energy. Additionally, the calorie is a common unit representing the amount of heat needed to raise the temperature of 1 gram of pure water by 1 degree Celsius. That's what this would be used for, is to measure the calorie. So this is just the introduction to these. We'll use these units regularly throughout our courses. And if you have any further questions, please let me know.